what we've dealt with so far is a single loop, right? With a curve that is closed as the boundary, right? So this was our D, and this is the boundary of D. So now, my question is, what do you do if we have a domain like that, or a curve like that, but then we have this random loop on the inside? So D is now everything in between these two curves. Okay, so now, as you can see, we kind of have a problem because that hole is not supposed to be there. But what we can do is simply, well, I guess hold on, let me see. I'll do it this way. So, sorry if you can't really see the arrows. So the arrows on the outside are going in the counterclockwise direction, and I'll call this C1 is the outer curve, and the inner curve is called C2. All right, that's what I'm going to name it, and it's going in the clockwise direction. Okay. That's the way it is oriented. So what we do in this case, when you have more than one, so this is when you have more than one simple closed curve, as the boundary of D, this is what you'll do. Boundary of D. So in this case, whenever you have something like this that's more than just this simple example, this is where you kind of have to really pay attention to the details and the directions that the arrows and the curves and everything are going. Okay? So in this case, what we want, remember as I mentioned before that whenever you're walking along the curve in the direction of the arrow, pretend you're the arrow, the domain, the shaded area, has to be on your left side. Okay, so let's look at the first curve. So we have C1, if we're going in the direction of the arrows, which is in the counterclockwise direction, as you can see, the domain will be on our left, right? The shaded region is on our left. So C1 is good. So the boundary of D is actually composed of C1, all right, so that's the outer one, and then we're going to add it to the boundary of, on the inside, right? The inner boundary here, which is C2. And the important part is whether or not we need a negative sign in front, okay? So let's see what we have. We have C2 going in the clockwise direction. That's the way it's oriented. And if we follow the arrows, we have to see if the domain is on our left side. So looking at this arrow in particular, the domain is already on our left. So C2 can stay as it is. We don't need to switch its direction. So that means we do not need a negative sign. Okay, so in this case, it would just be C1 plus C2. So the C1 plus C2 is the boundary of D because it's bounded on the outside and on the inside, right, on the inner one. So what this means in terms of the line integrals is now that, let's see, so the line integral over the boundary of D of f dot t ds is simply equal to the line integral, so f dot t ds over C1 plus the same integral, but this time over C2. Okay? So now let's look at a little bit more complicated examples so we get some more practice with this. So let's say we have another curve, but this time we have one and another hole. It kind of looks like a mask, like an 8. Okay, so the first one, the outer one, again, I'm going to call it C1, and it'll be going in the counterclockwise, so like this. Okay, so this is C1, and then we have a C2 in here. So C2 is this guy, and we'll have them going in the counterclockwise direction as well. And the last one here, I'll call that C3, and that'll be going in the clockwise direction. See that here? Okay. All right, so domain, again, this is in between, so this fills the mask, basically. So all in there, this is our domain D. Okay, so in this case, let's see what our boundary is going to be. So it's going to consist of 3 curves in some way. C1, a C2, and a C3, but we need to figure out whether or not to put a positive or a negative sign in front of each one. Okay, so let's look at C1. We have, following the arrows, we see that the domain, the shaded part, is on our left, right? As we go this way, it's on our left. So C1 is good. That's a plus sign. C2, let's look at that one. So we have it going in the counterclockwise direction. So if we follow the arrows, say our person is here, and we're going this way, on their left, we're actually in empty space. This is not our domain. So what we have to do is reverse the orientation. So that means adding a negative sign in front. Okay? And lastly, let's look at C3. So we have that going in the clockwise direction. So as we go around this curve here, we see that the boundary, the domain is on our left side. Okay, as we're going this way. It's on our left side. So that's going to be a plus, so that's good. Alright, so the line integrals in this case would look like the following. We'd have line integral over the boundary of D, so this is the entire boundary. We're considering it. And then this is going to equal the line integral over C1, and this is a positive one here, so like that. And then for the C2, we have to have a negative sign in front, so we're actually subtracting that one. Well, we're adding the reversed orientation of it, technically. So yeah, we're subtracting it. And then the last one, we're just going to add that one, because it was already in the proper orientation. So we'll put it as such. Okay? So again, direction matters. So we'll do an example of this on the next slide. Okay, so here's our example, and I'll write down all the givens first. So our given is, given that our vector field, F, arrow, is x minus y, comma, x plus y to the third. And our area, they're giving us the area of, let's see, what is it, domain, is equal to 8. All right, that's a given as well. And we're also given the picture, so I'll draw that here. So we have a picture, there's a circle in here with radius 1. So this is our unit circle, okay, and it's oriented counterclockwise. And then we also have some curve, some other outer curve, and that is C1, and we'll call this inner one C2. And this one is also oriented in the counterclockwise direction. Okay, so our domain is everything in between these curves, but not inside the little one. So this is our D. Okay, so we have this, and we're supposed to calculate. So here's our question. Calculate the following. The line integral over C sub 1. Okay, so C sub 1 is the outer one. So we kind of, let's see what we have to do here. We're going to take a little bit different approach. So, let's see. We do know that the boundary of D is going to consist of what? We have a C1, let's see, well, we have a C1 and a C2 in some way. We just have to figure out whether each of them are positive or negative. So let's look at C1. If we follow the arrows, we see that the domain stays on our left side. So that's good, so that's a plus sign. And then let's look at C2, our inner curve. If we follow the arrows in the counterclockwise direction, we see that the domain is actually on our right side. So that means we have to reverse the orientation of it and make it go the other way. So that means we need a negative sign in front there. Okay, so now let's set up, we'll use Green's theorem, and we have to use this relation here. So first of all, Green's theorem says that the line integral over the boundary of the domain, so f dot t ds, is equal to the double integral over the domain itself of partial f2 partial x minus partial f1 partial y, and then times our dA. So this is Green's theorem. Again, just a reminder, Green's theorem. Okay, but our problem here is that we need to concern ourselves with C1 only. So we're going to be dealing with the left side over here. Okay, and we'll be using the right side as well, but this is the focus here. So let's break this down into something else. So using this relation here. So our boundary of D was equal to C1 minus C2. So that means we could break it down into the line integral over C1. Okay, like this, and then subtract the line integral over C2. Okay, so something like that. And now we kind of just basically have to work with all of the information that we have here to sort out everything. So keep all of this in mind. Make sure you have this written down, and I'll move on the next slide. So actually, let's start with the double integral side. We'll start with the right side of the equation so that we can use it to figure out the left side. So the right side looked like this, right? We have our double integral over the domain, so of this thing. And later on, we'll figure out that everything in parentheses here is called the curl, C-U-R-L, but we'll do that in a future video. And then dA. So here, let's just compute, given the vector field x minus y and x plus y to the third, let's just compute what this integral is. So first of all, let's see what the d partial f2 partial x minus partial f1 partial y is. So if we take the x derivative of the second component, we just get a 1, right? The y to the third goes away. And then subtract the y derivative of the first component, which is a negative 1. So then that would just get us 2. So 2 goes in the parentheses. So then we get double integral of the domain of 2 and then a dA. So what we can do is factor out the 2 over here, put that in front. So we get 2 times double integral of the domain of 1 dA. And as you might recall, this thing here is equal to the area of the domain. So we actually have 2 times the area of the domain, which is really good because they actually gave us the area of the domain in the question, or in the problem. And that was equal to 8. So this is going to be 2 times 8, which is 16. Okay? So this is equivalent to the right side of the equation. But this is not our answer, right? Because this is equal to, so let's say, again, here's a refresher. So we have Green's theorem being the line integral over the entire boundary of the domain being equal to the top thing up here. So the double integral over d of partial f2 partial x minus partial f1 partial y dA. So this is what we found to be 16. So therefore, the entire line integral over the entire boundary of the domain is 16, but that's not what the question was asking for. The question was asking for the line integral only over C1. Okay, so this is where it gets a little bit tricky, and you have to pay attention pretty carefully. So we've gotten this far, and now let's save this information, and we'll continue with the problem. Okay, so now what we could do, so we have this relation of okay, I'm just going to say that this is the line integral, and then you can imagine the f dot t part here. So this is the line integral over the entire domain. That's going to be equal to the line integral over C1, and then we said that is minus the line integral over C2. Okay, so this is what we're solving for, the line integral over C1. So let's solve for that by adding the line integral over C2 to both sides. Adding line integral over C2. So then these ones cancel, and we get that the line integral over C1 is equal to line integral of the boundary of D plus the line integral over C2. So on the last slide, we found that this thing equals 16. Okay, this is equal to 16, but we don't know this one. So let's find this one, and then we can add that to 16 to get our final answer. Okay, so C2 again is as a refresher or as a reminder is the unit circle. So whenever you see unit, just think of 1. So unit circle oriented counterclockwise. Okay, so that means going in this direction, like that. Okay, so let's parameterize the unit circle. So our C2 of t is going to be equal to r times cosine t. So r in this case would be 1, so that would just be cosine t. And then for our y component, we just have a sine t. And then, hold on, close arrow thing. And then let's take the derivative because we're computing the line integral, so we'll need that. So we have C2 prime of t, and then this is going to be a negative sine t, and then a cosine of t. Alright, and t here, our parameter variable, the bounds for that are going to be 0 to 2 pi because we want to go all the way around the circle, right, to close the curve. Okay, so now we have, and again, I'll write the vector field. So our given vector field was, let's see, where was it? Oh, okay, so we have an x minus y and an x plus y to the third. Okay, so now what we're going to do is compute the line integral over C2, which is of f of c of t, and then dot that with c prime of t and dt. This is the definition of the vector line integral, right? So our boundaries are 0 to 2 pi, and then if we plug in x minus y, but the parameterized x minus y, so x of t is this thing, cosine of t, cosine t, and y is sine t. So this will be a cosine t minus sine, sine t. And then we have a cosine t plus sine to the third t. And then we have a big dot here, dotted with, sorry, I ran out of room, dotted with the c prime of t. Or, well, in this case, it's c2 prime of t. So that's just going to be our negative sine t, comma, cosine t. And then a dt at the end, of course. So we'll dot this out on the next slide. Okay, so what we get is 0 to 2 pi. And then when we dot it out, we get a negative sine t, cosine t, and then plus a sine squared t, plus a cosine squared t, and finally plus a sine to the third t times cosine t, and then a dt. So this looks like a lot, except for, again, here's the useful identity, that this all equals a 1, right? So we can simplify this into 0 to 2 pi, and then we have a 1 plus sine to the third t, cosine t, and then minus sine t, cosine t. All right? So something like that. And then you can go through and solve all of this out, except for we know that in integration, as I've explained in another video, I believe, in a previous video, when you have sine and cosine being integrated over a full period, so either that or that, right? Integration of sine something, I'll just put a theta here, of sine or cosine, oh, that's supposed to be cosine, or cosine over full period, and full period in this case for sine and cosine refers to 0 to 2 pi. So integration over that is just 0, because when you integrate on an actual graph, it turns out to be 0 for both of them. Okay, so basically what this does is it eliminates these two components here, because we have a single cosine t and sine t's here. So whenever you see sine something, cosine something, you can usually cross them out when you have a full period. But you should always check, do a logic check. Okay, so what we're left with is just a 1. So we have 0 to 2 pi of 1 dt. So this is just going to be t as t goes from 0 to 2 pi, such as 2 pi minus 0, which is 2 pi. Okay? So now I'll move on to the next slide to put everything together. So we have that the line integral over C1 is equal to the line integral over the entire boundary of D plus the line integral over C2. So we found this to be 16 and this to be a 2 pi. So our final answer is going to be 16 plus a 2 pi. Alright, so that's it, and even though that seemed like a long problem, it kind of was, I'm not gonna lie, but it's good to see how you can kind of problem solve in a way. Just take the components of things that you know are equal to each other and relations such as this one of the entire boundary and how it's related to each of the curves individually, and it's good to piece together the puzzle in a way to get our final answer. Alright, so that's it for this video, and good luck on your homework, and I'll talk to you in the practice problems video if you watch.